Okay, last time we did two sample means problems when you have dependent samples. Now just remind me, what do we mean by dependent samples? Okay, there's a relationship of some kind between them. Almost always, what is that relationship? What'd you say, Amy? It's the same person. So usually, you can tell whether or not they are independent samples based on did they use different people or not. If they use different people, then they're independent samples. If they use the same person or thing, then they're dependent paired samples. Okay? So, any questions over that material? You have homework due tonight on section 10.4. Yeah.
Will we have homework due next Monday too, or will we do a chapter that day?
We will do one new section on Monday, and that is section 11.2.
And will there be homework over it?
Yeah.
Okay.
Yeah. It's actually really short. I think there's only 2 homework problems, but there will be a short homework set over 11.2. This slideshow, I'm not going to show all of it, but this is what I post for my online students. This is what they get instead of a lecture if they don't choose to watch the videos. But this is one of the homework problems that you'll encounter if you haven't already that's due tonight. And this one is out of the book. It's number 1049 on page 512. And you'll notice that you have 10 students, and they were asked how many times during the previous year they did each of these 3 activities. Go to the movies, go to a sporting event, or go to a party. And they want to know, is there a difference in the mean number of movies and the mean number of sporting events? Okay, so that's this column compared to this column. I've been getting a few email questions from people over this. The main one that I'm getting is, I've tried to do this in my calculator, and for some reason I'm getting the wrong answers. I used 2SAMP-TINT, and I'm not getting the right thing. What should you be using here? T-interval, not 2SAMP-TINT. When do you use 2SAMP-TINT? When they're independent samples. Are these independent samples? No, because the same person, student number 1, said, I went to the movies 10 times, I went to the sports 5 times, and I really liked the party 25 times. Right? So they each of them answered 3 things. I've also been getting a few questions, not very many, but a few saying, what do I do when there's 3? I'm used to there being 2. Well, you ignore the 3rd one, right? We are only comparing 2 at a time, so you compare the 2 that are being asked. In the book, they have you compare movies to sports, and then in the next question they have you compare sports to parties, I think, or whatever. So you just use the 2 that are being compared at that time. You ignore the 3rd one, so that's extraneous information. So what is the strategy? If you don't use 2SAMP-TINT on this, what do you do?
The difference between each for your data.
You first compute the difference. Now what they're asking for is movies and sports, so we can ignore parties. Although I thought it was kind of interesting, the parties. Right? You see anything interesting in the party data?
52.
52.
2 people.
How many times? 2 out of 10 people said, I went to 52 parties last year. That's once a week. Now you'll see things like that in data where probably what happened was they asked the person didn't actually count how many parties they went to. They probably said, well, I go to about 1 a week, and there's 52 weeks, so 52. Right? So you get these spikes sometimes if you did a histogram at certain values where people tend to round things off or whatever. So they may not have actually gone to 52. They may have missed a few weeks in there, but they probably, on average, they go to 1 a week, so they called it 52. They may have actually been higher than 52 because there may have been some weeks where they had more than 1. right? So, who knows? But it is kind of funny that that just completely blows away the other two columns, right? So, these are college students, I guess. So, the strategy then is to take the difference. So, on the next slide, I show the difference pasted over the top of where the parties were before. Now it's the difference. So 10 minus 5 is 5. 4 minus 0 is 0, and so on. Then what's the strategy? Now you do t-interval or t-test on that column only. Okay. This will be the source of many missed points on the final, is people get this data set in a problem and they do a 2-samp t-test instead of a t-test on the differences. Right? Yep.
Why is it if we, since it is actually a negative number, why do we get a wrong answer with the negatives?
You shouldn't. You need the negatives. Yeah, the negatives should be there. Because if the null hypothesis is true, what would you expect these differences to be? 0, right? But you know there's going to be some random variation from person to person, so what you expect to see then is that they average out to 0. There'll be some negatives, some positives. Okay? So, no, you do need the negatives. So if you're getting...
Well, I think when we did that, the pulse thing the other day, when I was putting in the negatives when we got the difference for number 2, and I was getting something different than what you had wrote.
Okay, yeah, I understand. What was happening there was we did the pulse one in class, and every single one was either positive or negative, depending on which direction you did the subtraction. So you were getting something different because you probably reversed the order of subtraction, and you would have gotten a negative sign on your test statistic and on your confidence intervals. Be the same numbers, but they'd have negatives on them and they'd be reversed, right? So then you probably figure, oh, I got to ignore the negatives in order to match what he's doing, right? But here, if you subtract in the other direction, then this one becomes negative, negative, positive, positive, but you need those negatives. You need what the difference is, positive or negative. Okay? That example with the pulse just turned out that nobody went down, everybody went up in their pulse when they stood up.
So one more time, you said it is not a 2-samp.
It is not a 2-samp t-test. It's a t-test. I wish the calculator had said 1-samp t-test and 2-samp t-test, but it doesn't. It just says t-test, and that's your 1 sample, and then it goes to 2-samp t-test. So you want the t-test.
Just the t.
Right. So what you're going to do is you're going to enter those differences into a list, and then this is how to get a confidence interval. You push the stat button, test, and t-interval, and then you'll get this interval, right? And you should be able to confirm that. Now, one thing I intended to show in class, and I didn't get it done, I forgot. It is possible, let me go back to the data. It is possible to make your calculator do the subtraction for you. Particularly if you've got a lot of data values, there's an awful lot of chance that if you're just doing the subtraction in your head, you'll mess one of them up, right? So always let the computer do menial tasks like that that are error prone when we try to do it ourselves. So one thing you can do is enter the movies into L1 and the sports into L2. So you go 10 and 5. So get out your calculator. I'll do just the first 4 of these. And enter the first 4 of these into L1 and L2. Now to make the calculator compute the differences, you can go arrow over till you're in L3 and clear that list out. Okay? Everybody got it cleared? Now, arrow up so that the L3 is highlighted up at the top. And then press enter. and you should get a blinking cursor down here. Everybody see that? Now you can type in L1 minus L2 and press enter, and it'll compute those differences, right, and put it right in there. Isn't that cool? Now, I don't know if it happened to anybody in here, but in my last class, somebody went, hey, but it didn't work for me. I got a DIM mismatch. That stands for dimension mismatch. And they typed in the first 4 numbers without first clearing it, and one of them had more stuff down here. So they didn't have the same number in the 2 lists, so when it tries to do it, it's saying, well, some of these don't match up, so I can't do it. So that's a dimension mismatch.
Can you say what you did?
Okay. Enter the data. Then when you get into L3, you arrow up. Like when you first get in there, your cursor will be blinking on that first one. Arrow up, and it'll highlight it. Then press enter. And then you'll get a blinking cursor down here at the bottom where you can type in some kind of an expression. And so then just type L1 minus L2 and press enter. And it does all of the differences. Okay? Okay, any questions on that?
So when you go to T-test in the calculator, we just put in like movies first, and then next time we go into sports.
No. When you go to t-test, you put in the
Oh, the
differences.
differences, okay.
Right.
Okay.
So what you're going to do, and I think that's on the next slide, that's interval, but there's the t-test. There's the next slide. Right? If you're going to do a hypothesis test with the differences, and here I said in L1, whereas I had you put them in L3, but just wherever you put them, you go to t-test, select data, and then you tell it where your data is located. List
Okay.
is L3, right? And you'll want to enter that mu sub 0 is 0. Now where did I get that 0? Right, that means no difference. That's the null hypothesis. So mu sub d for mean difference, here it is, mu sub d equals 0, that's my mu 0. Okay, so that goes in here. Then list is in whatever list you put it in. There's a line FREQ for frequency. Leave that as a 1. It should already be a 1. Don't ever change it, because if you change it away from a 1, it's kind of tricky to get it back. So it's always going to be a 1 for us. Select the not equal symbol and press calculate, and you should get a p-value of 0.4540. What is that p-value telling you? Do not reject the null. So what does that mean about movies and sports?
There's a possibility that there's no difference.
Good, I like how you said that. There's a possibility there's no difference in the mean number of times people go to the movies and sports, right? The confidence interval should tell you the same thing. Does it? Negative 7.56 to 15.56. Does that tell you the same thing? Yeah. 0's in the interval, so 0 is plausible. There might not be any difference. It doesn't say the difference is 0. It says the difference could be 0. Okay? All right. That's a quick review of the homework problems that you're going to be doing that are due tonight. Okay? So section 10.5 is called How Can We Adjust for Effects of Other Variables? Okay? So this is back to the old idea of a lurking variable. Oh man, I remember that from chapter 0 or somewhere. What is a lurking variable? Okay, it's a variable that has an effect on the variable of interest, but is hidden or unknown, right? So they have a good example here in the book. Oh, I wanted to say this too. This says skip the middle of page 507 to the end of the section. That's the stuff about proportions, and I told you that last time, that I'm only doing the means because I ran out of time. So comparing proportions from 2 paired samples, we just aren't going to do. So you're allowed to stop reading when you hit the middle of page 507. Okay, now, here's an example. It says, teenagers who watch more TV have a tendency later in life to commit more aggressive acts. I'm not making this up. That has been shown with data. That teenagers who watch more TV tend to commit more aggressive acts later in life. So what is it about TV that's ruining them? Okay, depends on what you're watching. Could there be some lurking variable that says, well, it's really not the TV that's causing the problem, it's just the TV watching is another symptom of some other problem? Can you think of something else? Lack of supervision. Okay, lack of supervision might lead to more TV watching and to not being raised right and not being very socially, what's the word I want?
Adapted?
Yeah, socially adapted. Good, I like that. Mean. Make them mean. So, you know, there's parents out there that use the TV like a babysitter, right? So they plop their kid down in front of the TV, and of course these are teenagers, but you know that thing can manifest itself through teenage years. So you know, parental neglect might be the reason that they're more aggressive, but watching more TV is something that is caused by that as well. So that would be a lurking variable. Now I'm overstating things just to make the point, but here's another suggestion. Teenagers who watch more TV tend to attain lower educational levels, and perhaps lower education tends to be associated with higher levels of aggression. Could you think how that might happen? Okay. They get poor grades in school because they're watching too much TV, because they're not being supervised, right? They're not being told, get your homework done. As a parent, I can tell you, you have to say that once in a while. Get your dang homework done. Turn off the Xbox. And see, this is probably old data. It's TV watch. Now it's not TV anymore. It's video games. But it's the same idea. Right? They get lower grades, so they don't do as well in school, so they become low self-esteem. They think, well, I'm not very smart, so they don't go to college, blah, 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 blah. So later in life, what happens? They don't make as much money, which causes stress, so they hit their wife. Whatever. But you get the point, that there could be lots of reasons. So what we want to do when we analyze data like this is try to somehow account for these other things. Like maybe do an analysis of number of hours of TV watching as a teenager and its effect on aggression, but control for what educational level they are. So analyze for those who did not graduate high school, and then analyze those who graduated high school but didn't go to college, and then those that got a college degree, and so on, right? So that's one of the main strategies to control statistically for a variable. Now, technically, by the definition, you can't control for a lurking variable during the data analysis. This is called statistical control. Right? There's experimental control, but what we're talking about today is statistical control. What's the difference?
Design your study around lurking variables.
Okay? If you design your study around lurking variables to remove them, like doing a crossover design instead of a two groups design or whatever, that's experimental control. So what's statistical control? That's controlling for the variable during the data analysis, using the values of some variables to help try to explain why other variables. That's statistical control. Both are important. But if you design your study correctly and do experimental control really well, then you usually don't have to do statistical control. Sometimes this is statistical control is a band-aid to try to fix something that went wrong before. Right? But technically you can't control statistically for a lurking variable, because the strict definition of a lurking variable is it's unknown. It was not collected. So if they didn't collect educational level of these people committing aggressive acts, then we can't go back and adjust for it in our analysis. So we have to think of those things during the design phase and make sure we collect that data so that we can control for it. Then it's not called a lurking variable anymore. Does anybody remember what it is called? And I didn't really stress this definition back then, but there was another word. They said it's a lurking variable if it's not collected, but if you collect it, then it's called a, nobody? Confounding variable. Remember that word? I probably only said it once during class, if at all, but it is in the book. So you'll hear statisticians talk about doing analyses where they control for confounders, and that's what they're talking about. Okay? So this last bullet says, a variable that is held constant in a multivariate analysis is called a control variable. So that's what I was talking about. Hold educational level constant. Analyze within those with low education, within those with medium education. Right? So you hold it constant and do an analysis. Okay, I'm going to skip past this and we'll go to an example from our class survey. In our class survey, we collected data on pulse, smoking status, and exercise. And we've done a little bit of analysis now with that. Last time I showed you some, I think I had to do it on the board, right, because the computer wasn't working, but I had the numbers for average for smokers and average for non-smokers. And then we did the same thing for exercise and non-exercise. Do you remember the results of those analyses that we did? Here's smoking. Non-smokers, smokers. So no, yes. Right? The average for non-smokers was 70.6 beats per minute, average heart rate. For smokers, it's 76.98, so basically 77 beats per minute. A fairly big difference. Right? 6.5 beats per minute difference. Was it statistically significant?
Yes.
Here's the confidence interval. Now, how did we get that confidence interval?
The differences in the t-test.
Okay. And where do we go on our calculator? Is this t-interval? Or is this 2-samp t-interval?
Two samples.
This is 2-samp. Why?
Because you're comparing two groups that are independent or dependent.
Yeah,
It's one of those two.
that's right. It's one of those two. Now I'm asking you which one.
Independent.
Independent. You just guessed, but you guessed right. Independent. Why are they independent? They're different people. You can't be a smoker and a non-smoker. So we had to measure a different set of people for one group than we did for the other group. So they're independent samples. So this is a 2-samp t-int problem or 2-samp t-test problem. Okay? So we don't take the differences and analyze the differences. Okay? So here's the confidence interval, 3.43 to 9.27. Interpret that interval for me. All together now? We are 95% confident that the true difference in the means is in that interval. Nobody in our study had a heart rate of 3.4 or 9.27. We hope not, right? But that's the difference. The average difference is somewhere between 3.5 beats or 3.4 beats per minute and 9.3 beats per minute. Okay? Since what is not in there
0.
Since 0 is not in there, we say there is a statistically significant difference. Smoking heart rates are higher. Okay, so that's down here. And here's the p-value for the test if we did a hypothesis test. So we reject, no difference. Smokers have higher heart rates. Right? Now remember, we also looked at exercise. Here's the data by exercise. So if you remember, we had 148 who said they did not exercise and 237 that said they did. If you add those together, there's your 385 observations we had in our data set. Right? And here's the average pulses. Just the eyeball test, you can look and say, well, those who exercise have lower average heart rate. But it's not as big a difference as it was for smoking a minute ago. Right? That one was a difference of almost 7. This is a difference of a little more than 3. Right? But is it statistically significant? Yeah. Same thing, confidence interval 1.52 to 5.66 does not contain 0. P-value, highly significant, way less than 0.05. So there is strong evidence that exercise have lower heart rates. Okay? But think back to chapter 3 when we did contingency tables and we looked for association between two categorical variables. I've got two categorical variables here, smoking and exercise. Was there an association between those variables? Was there a relationship between whether or not somebody smoked and whether or not they chose to exercise?
Yes.
Yeah. Now see, everybody nodded when I said it that way. A minute ago I said, is there an association between those two variables? I went, you just have to learn the lingo. What do we mean by association, right? So, yeah, there is an association. And here's the analysis of that data. Remember contingency tables? Have I mentioned that the final is comprehensive? There you go. Right, here's my 148 who don't exercise, 237 who do. Here's my 322 who don't smoke. Here's my 63 who do smoke. But now it's cross-tabulated by who falls in both of those categories. This has the number 67.39%. What is that called? Where did that number come from?
Taking like the 217 divided by the total.
Okay, good. 217 divided by 322 is 0.6739, which as a percent is 67.39. What is that called? Because I may ask you to do this, and you have to know what I'm asking, right? What did you say? Conditional proportion. That's a conditional proportion. So the conditional proportion of exercisers among non-smokers is 67%. 2/3 of the non-smokers said they exercise. Whereas 31%, about 1/3 of those who smoke said they exercise. Now back then we didn't have any kind of a statistical test, right? We did the eyeball test. We looked at those numbers and went, ooh, those are different. So there is an association. But now we're sophisticated enough to do a hypothesis test. Tell me what hypothesis test you would do here. Difference between what? Difference
The
in
people
two.
who exercise and non-smoke and the people who
Okay.
smoke and exercise.
That's exactly right, but here's the question I want you to answer first. Is this a means problem or a proportions problem?
Proportion.
This is a proportions problem. Is it one sample or two?
Two.
Two. This is a, on the calculator, two, not SAM, that's means, to prop, Z, int, or test, right? So do that real quick. Do a 2 prop Z test and see if there is a difference in those two conditional proportions. A statistically significant difference. We know it's going to be because look how far apart they are. Jory, you looked up and went, I got way more numbers in this table than my calculator's asking me for, so which ones am I supposed to enter? What's x1?
217.
217. What's n1? 322. So I've underlined the numbers you need, right? What about this column? Where do I use those? Well, I don't. I can ignore it. That's redundant information. If I know that 217 out of 322 were successes, then there had to be 105 failures. So I could equivalently compare these two proportions, but you get exactly the same p-value as comparing these two proportions, because it's redundant information. So using these four numbers, x1, n1, x2, n2, what was your z test statistic?
5.32.
5.32. Is that big or little? That's huge, right? It's a z, so that's a z-score. That's number of standard errors away from the null hypothesis. What's the p-value? It must be one of those e to the minus something p-values.
1.05
To the negative 7th. So 1.05 times 10 to the negative 7th. There's the p-value. So there's a very strong relationship between smoking and exercising. So where am I going with this? Is it really the smoking that's causing people's heart rate to go up? Or is it just because those people who smoke don't exercise? So they don't get the benefit of lowering their heart rate. In other words, is exercise a lurking variable that makes it look like smoking causes your heart rate to go up? Or does smoking cause an increase in heart rate independent of exercise? How in the world am I going to answer that question? Hopefully with a calculator. Yeah, we will use a calculator. But just in general, what's the strategy? What did he say to use for statistical control of a variable? Okay, it's a confounding variable, but then how do we analyze?
When you're doing data analysis.
Okay, I want to know, what am I going to enter in my calculator? How am I going to analyze this data? Caitlin, you got an idea? Yes, you do. Come on.
Would you maybe do it if you're, like, maybe how we did the conditional proportions where we do this given something else happens?
Okay, good. That's exactly what you're going to do. We're going to look at these numbers for smoking, but condition on, well, they're not the exercise, right? So what I want to do is I want to say, well, I want to get non-smokers and smokers, but only from those people who don't exercise. So then there can't be this confounding between exercise. Take only people who don't exercise. Hold that lurking variable fixed. Then look at smoking versus not smoking within that subgroup. And then you can also go the other way and say, okay, now let's look at people who do exercise. I'll have some of them that are smokers and some of them that aren't smokers. Let's compare them. So I'll do two analyses instead of one. I will hold the level of exercise fixed. Okay? So here we go. There's the data you need. I've broken down the other table based on conditioning on whether they exercise. So here's my 217, add these two together, 237 people who exercise, and here's my 148 people who don't exercise, but split out by whether or not they smoke, right? So you might recognize these four numbers as the ends that were in that contingency table, okay? then I get the average for those 105 people that were in that one cell of the table. I get their average pulse. Right? So I compare the means within columns by exercise or not exercise. So here's what we're going to do. We're going to split the room right down the middle, and you're going to go this way. No, you're not, because I'm going to split you from your friend. You're going to go this way. Okay? And everybody over here, I want you to do the top one. I want to know, is smoking... No, let me start that sentence over. Is there a significant difference between heart rates, average heart rate, between smokers and non-smokers holding exercise fixed at yes, they exercise? So that's the top table. The other half of the room, I want you to do this bottom one. Is there a difference in the mean pulse for smokers versus non-smokers among only people who do not exercise? Do those tests. And what I'm going to do is I'm going to collect your answers in the form of a p-value and a conclusion. In both cases, we are testing the null hypothesis that the mean of smokers, instead of 1 and 2, I'm just going to write it out. Mean of smokers is equal to the mean of non-smokers. Right? Do a two-tailed test. Yes?
You can see if I'm doing it right.
Can I see if you're doing it right?
Yeah.
Sure.
I think I am, but I don't know. Okay. That's right, and then
That is not.
we have to do the 2.
Yeah, it would be a Z.
Oh, yeah.
Yep. Whoa. I don't either. You've got some kind of a fritz in there. It's probably a low battery situation. Then you have a memory here. See if you can just type over and it'll start working. No, you want stats. Then just arrow down. Okay. You may have to clear your memory. You may have too much in there. Okay, that is correct. You got the same thing? Yeah, that is correct. Yeah, I want the p-value. And where's your calculator? Okay, that is correct. That you did an confidence interval, but it looks correct. That is correct. Okay, good. 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 Okay, that side of the room all looks like they got it figured out. Okay, it looks like you're doing it right, so go down and finish out. Get your p-value.
Oh, I guess I never put calculator.
I'm confused about, like, right here, where you plug in 1 and 2, like, I put the, but I don't want to.
No, you did it right.
Okay.
You want to just use the ends that are for that subgroup. You get it? Okay, you're going to do 2 SAM t-tests. Yeah, because these are independent samples. Confused?
No, I typed.
Yeah, that is right. Okay, so here we go. Among the exercisers, what was the p-value for that test? 0.001, and it was a 0.05 or something, right?
Yeah, 06.
Okay, so what's the conclusion?
There is a difference.
Conclusion, there is a difference between smokers and non-smokers in heart rate. And that's saying those people exercise. So exercise is not, you can't say, well, it's because the smokers didn't exercise and the non-smokers did. because here everybody did. So exercise is taken out of consideration. Then you do the other one, and so this is the non-exercisers. What's that p-value? 0.041? 422, like that? Okay. So what's the conclusion there? Hello? Is this less than alpha? Yeah, but barely, right? It's barely significant, but it is significant, right? So same conclusion. Same conclusion. So no matter which way I cut it, if I look at only those people who don't exercise and then divide them into smokers and non-smokers, I get a statistically significant difference between them. So smoking is different. Now, notice I stopped just short of saying smoking causes an increase in the heart rate. Statisticians are real reluctant to make definitive statements like that, right? Because there may be some other thing that's, some other lurking variable I haven't thought of. So demonstrating cause and effect is very difficult, particularly from an observational study like this. But at least I can answer the question that was posed here. Is exercise a lurking variable that makes it look like smoking is an important variable? And the answer is no, it's not. Exercise has been controlled for, and we still see a difference between smoking. Okay? So we can rule that out as a lurking variable. I haven't ruled out other possible lurking variables, but I've ruled that one out. Now, suppose we wanted to go back and do an experiment and conclusively say that smoking causes an increase in heart rate. What would you have to do? What kind of an experiment would you have to conduct? A crossover study?
Yeah, someone might be on and off smoker or not.
It'd be hard, wouldn't it?
Yeah.
So how would you do this?
Take a random sample of smokers and a random sample of non-smokers, and then separate them out to see if they exercise and if they don't exercise.
Okay, that's almost, except we didn't use random samples. That's basically what we did here. So that's not going to prove causation because there could be other lurking variables. I want and that was an observational study. I want an experiment. What do you have to do as an experiment,
You
Wayne?
have to just take a group of non-smokers who are all kind of similar in lurking variables, and then make them start smoking and measure their heart rate.
Exactly. Did everybody hear that? Take a group of non-smokers who are all similar for all these other lurking variables, and then make half of them start smoking. Now that's a hard study to pull off, right? Anytime you do research, particularly research on human subjects, you have to get what's called IRB approval. Have you ever heard of that? If you've done any of your classes here at Washburn where you have to do research, you'll probably have to deal with. They may not call it IRB, but IRB stands for Institutional Review Board. There has to be a research board who says, yeah, your study's okay, you can go do it. So they're looking for putting subjects in danger. They don't want you doing things to people that could harm them in some way. So they have to approve it. So making somebody start smoking, that could harm them, right?
Could do the opposite and make them stop smoking.
Yeah, see that's a good thought, because you could think, well, I'll go the other way. I'll take a sample of people who all smoke, right? But maybe all of them smoke, but they've all expressed an interest in quitting. Like, I would like to quit. Okay, what we're going to do is we're going to randomize, and we're going to say, this group, we're going to help you quit smoking within the next 6 months. The other group, we won't help you for 6 months, but then we'll help you after that, right? So then you collect that 6-month data on those. You do baseline heart rate, and then after 6 months, those that have quit, you see if their heart rate went down, right? And those that are still smoking, you compare those groups, right? But then again, to get approval to do the subject, you can't exclude somebody from treatment when they've asked for treatment. So you say, well, you have to wait 6 months, but then we'll help you quit. But then you can use their data also to supplement, the drop in heart rate. And that would pretty conclusively say that yeah, it is the smoking. Because you've controlled for lurking variables, even unknown ones, because you're measuring the same person twice. Here's their heart rate while they're smoking. Now here's their heart rate when they're not smoking. All other variables should be controlled for. Now you have to be careful and make sure that nothing else changes. Now don't go changing your diet. Don't start exercising. Just quit smoking. Nothing else. Right? So you have to be careful with those kinds of things in a study. Okay. That's all the time I have. So homework due tonight is section 10.4. That's the paired samples means problems. And then Monday will be this section 10.5. And there's only 3 problems in that section, I think. But, and then one day next week we will learn section 11.2, and then the other 2 days we'll spend reviewing for the final. All right, we'll see you then. Have a great weekend.